Alright, so we're now ready to put together all the ingredients that we've seen so far, two universal families of hash functions, extractors, and a pretty good measurement, in order to give a construction and analysis of our first quantum-proof strong seeded extractor. So let's go for it. First, let's remember the construction of an extractor based on two universal families of hash functions that we saw a few modules ago. So what were two universal families of hash functions? These are functions that map n bits down to m bits, and the two universal condition is that when I choose a function at random from my family, then for any two x different from x prime and any two z and z prime, the probability that the function maps x to z and x prime to z prime is exactly the probability that any two completely uniformly random elements would happen to match z and z prime, which is 2 to the minus 2m, the square of the range of the functions. So that's two universal families of hash functions, and we saw constructions of such functions as affine functions over a finite field. And now, given any such family, I can define an extractor which takes as input a source, x, that is going to be a n-bit string, on which I have a condition on the min entropy. The min entropy of the source should be at least some bound k. It takes as second input a seed y, which is uniformly distributed over all d-bit strings, and that seed I'm going to use as an index for a hash function fy applied to the source x. And the goal is that the joint distribution of the output and the seed z and y, this should be statistically indistinguishable from the uniform distribution on the source and the uniform distribution on the seed. So that's the requirement for a strong extractor. And what we showed is that in the case where there is no side information, you could prove what's known as the leftover hash lemma, which says that if H is a two universal family, then this construction is a good extractor. It's a k epsilon strong extractor, as long as the input min entropy is large enough compared to the number of bits that we're trying to output. So this is all to recap. Now what we're trying to achieve is obtain the same kind of result, but now when we take quantum side information into account. So I just copied the same desiderata from the previous slide, except that now the min entropy of the source is measured conditioned on quantum side information E, and we also want the conclusion to hold conditioned on that side information, meaning that we want the output z to be uncorrelated from the seed y and the side information E. So now, if you express this condition, this approximation here is measured in the trace distance, you can rewrite it as saying that the sum of, so there's a little bit of notation here that I'm going to introduce for you, of these states ρ zy, their distance from the average density ρ is less than epsilon. What are these states? So I can define ρ zy to be equal to the sum over all x that are mapped to z by the function fy of ρ x e. And the density ρ e is simply going to be the average over the choice of a random seed y of ρ z y. Note that this could a priori depend on z, but because my functions are two universal, in particular they're one universal, you can check that in this way I always get the same density matrix ρ e independently of z. So if you rewrite this condition explicitly here, where the distance would be measured up to error epsilon in trace distance, then you get exactly the condition that I've written here. And so now we're going to try to perform the analysis and show that this condition is satisfied for some epsilon that's going to depend on the parameters of the problem. So let's see how this can be done. We're going to do it in two steps. The proof is very similar to the proof that we already saw analyzing the security of the two universal hasher against classical side information. So I'm not going to give you the details because it's very similar, but just to go over the two steps. First, we're going to relate the security criterion that we care about, the bound on the trace distance that we looked at in the previous slide, to an analog of the notion of collision probability that we introduced for classical probability distributions. That's the first step. And then the second step goes ahead and bounds this quantum analog of the collision probability as a function of the min entropy of your source. That second step of the proof uses ideas that are very similar to the analysis of the success probability of the pretty good measurement that we saw a couple of videos ago. So just to spell them out in a little bit more detail, let's do the first step first. So our starting point is that we want to get a bound on this quantity, the trace distance between the output of the extractor, so Z, Y, E, where E represents the output of the extractor on the source X given the Cy, so the distance between this state and the ideal state, which is uniform on the output, tensored, should also be uniform on the seed, tensored remaining system for the eavesdropper. So that's the quantity that we want to bound, and we expressed it in the previous slide using the trace distance and using these states, post-measurement states Rho Z, Y, that represent the adversary's side information when the extractor has been used with seed Y and produced the output Z. So when you can show using very similar arguments to what we saw in the classical case, you can bound this quantity. Let me just give you the result without showing the details. What you obtain is there's a prefactor of 2 to the output length of the extractor over 2 minus 1. This minus 1 here, don't worry too much about it. It's a normalization factor that comes in when you switch from trace distance to the notion of distance that we're using here. So don't worry about this minus 1. And then what you get is a larger expression, and let me write it for you. So this is the expression that you get. You can see syntactically it's really exactly the same thing as we had in the classical case, where now you can interpret the quantity that's in front here as a collision probability. We could call this Cp of Zy, and it's really the collision probability that's associated with the adversary's side information on Z and Y. So if these were one-dimensional, so that each state Rho Z, Y here corresponded to a probability, the probability of selecting the seed Y and having selected that seed obtaining the output Z, where the probability is taken over the randomness that's in the source, then you recover exactly the collision probability as we learned it before, simply the sum of the squares of the probabilities. That's a direct quantum analog. So now let's go to the second step. The second step consists in obtaining a bound on this collision probability. Again, let me not work through all the calculations for you. You can check them out in the lecture notes. They're given in detail. Let me just tell you what the result is. The bound that you obtain on this collision probability is that you can upper bound it as a sum of two terms, where the important part is the apparition of the appearance of a term here which depends on the initial conditional min entropy of the source, right? So this k is the same k that we had here. So you obtain this bound, and then plug it back in from the first line. What do we get? We get that the main quantity, the R, so of the extractor, this D quantity is at most, and what do I get? So m by 2 minus 1, then you have this collision probability multiplied by 2 to the D minus 2 to the minus m, so the first term here will go away. We're left with the second term that has been multiplied by 2 to the D. It's inside the square root, so I get minus k by 2. If you recall, this is exactly the same bound that we obtained in the classical case. As a consequence, we've now obtained a quantum analog of the classical leftover hash lemma, so let me spell it out for you. Here's our quantum proof leftover hash lemma. And it says that if you use an extractor that's based on a two-universal family of hash functions, you define the extractor as we did earlier on, then this is going to be a k epsilon strong quantum proof extractor now for any value of the initial min entropy that's at least the output length that you want to produce, plus a minor dependence on the security of the extractor. That's exactly the same dependence as we obtained for the two-universal hash lemma with no side information at all. So it's a strong result in that respect. It suffers from the same drawbacks that we already pointed out when we analyzed the classical variant, but it's going to be more than sufficient for our purposes. And so now if you combine the lemma, this security proof of the extractor, with the method that we saw to use extractors for privacy amplification, we have a complete protocol for privacy amplification that's sound against quantum adversaries. And this gives us the first building block in our protocol for quantum key distribution that we're going to see next week, where privacy amplification will form the last step in these protocols. So we'll learn about that soon.